Good day mga bayaws. Today here I will be discussing here the chapter 6, the gas and vapor cycle. Here we have a problem stating that in an Otto cycle, air at 1 bar and 290 Kelvin is compressed isentropic ally until the pressure is 15 bar. The heat is added at constant volume until the pressure rises to 40 bars. Calculate the air standard efficiency and mean effective pressure for the cycle. So first we have to determine what are the given. Here we have the pressure 1 at 1 bar, which is equivalent to 100 kilonewton per meter squared. Next we have our temperature 1, which is at 200 Kelvin. The pressure 2 is at 15 bar and convert it to kilonewton per meter squared. We will have 1500. Next is our pressure 3 at 40 bar and convert it, we will have the value of 4000 kilonewton per meter squared. And for the CV, the specific heat ratio at a constant volume, we have 0.717 kilojoules over kilogram Kelvin, and our universal constant, which is 8.314 kilojoules per kilogram Kelvin. Here, first we will have to solve the universal constant, which is the 8.314 kilojoules per kilogram Kelvin. And we all know that the specific heat ratio is its formula is the Cp over Cv, which is the specific heat at constant pressure over the specific heat at constant volume. Here is Cp is unknown. Then the formula for getting the R is equal to the M multiplied by the R. Since your air molecular weight is 28.97, so plug in the values, we will have our given values here at 8.314 kilojoules per kilogram Kelvin, and our molecular weight of oxygen, which is 28.97 multiplied by the R. So plug into your calculator using the shift solve to get the value, and we will have an answer of the R is equal to 0.2869. Since gas constant is R is equal to Cp minus Cv, we have the value of R, which is 0.2869, and our Cp is the unknown, and our Cv is given, which is 0.717 kilojoules per kilogram Kelvin. Plug in the given values and we will have the answer of the specific ratio at constant pressure, which is equal to 1.0039 kilojoules per kilogram Kelvin. Here we have next is we have to find the specific heat ratio. We have the values of the constant specific heat ratio at constant pressure and the specific heat ratio at constant volume. Plug in the given values and we have our specific heat ratio, which is equal to 1.4. Next is here the R is unknown, and we will be using the formula of R is equal to the V1 over V2 is equal to P2 over P1 raised to 1 over the specific heat ratio. Next is to plug in the given values. We have the 1500 over 100, all let's close this with parentheses and raise it to 1 over 1.4. and we will be given the value of 6.919. Here we have to find the standard efficiency, the air standard efficiency, which is equal to 1 minus 1 over the our R, which is 6.919, and we will be given a value of 3.87%, and that will be our air standard efficiency. Next is to find the mean effective pressure. And lastly, this is the last thing we need to solve. Here we have the mean effective pressure at PM is equal to P1, then multiplied by R, then K1, then R raised to Y minus 1, then minus 1, closed, over the specific heat ratio minus 1, then our R minus 1. So plug in the given values. We have the our pressure 1, which is 100, then the our R, which is 6.919, then the 2.67 minus 1, and our 6.919 minus 1. All over that is the 1.4 minus 1, which is our R, multiplied by 6.919 minus 1. Then calculate it, and you will have the answer of 569.922 kilonewton per meter squared.